Thank you so much for this kind introduction, and thank you for all for coming here and for this invitation. I'm also a senior researcher at CWI, like Martin, though my talk will be a little bit different than his in flavor. But I hope it will be interesting for this audience as well, right? So what we are going to talk about today is look a bit at challenges that we face in our energy systems and how AI, in particular distributed AI and multi-agent systems that are my core research area, can help us address some of these challenges through some examples and so on. Right, so first of all, let me just see. Oh, yeah. A bit about energy systems. Some people call them the most complex man-made system. The fact that I really like to mention in these talks is that if you don't know something about the country, so if economists don't have any real data about the country, they can just look at the energy consumption, and then they can get a lot of information from there. The picture that you see here is a famous image from that came out from NASA a few years ago. You can see. Oh, can we have a pointer here? Yeah.
It's a digital one, so you just press it and move it around.
Oh yeah, it should work. Yeah. So here you can see South Korea, the Chinese coast, and there's like a black hole there. So you can clearly, we don't have any good data, economic data for North Korea, but clearly they're not doing that well, right? So one thing to ask, and people do ask, is, okay, we have energy systems. Sure, they work. They've worked well for 70 years in most of the world. Why do we need AI? What is the problem? And the answer to that is that yes, indeed, energy systems are efficient. They have been designed to work efficiently, but under some very specific assumptions, which are no longer which are kind of breaking down in current energy systems. So they've been designed basically with a top-down approach. There will be a few large generators. Everyone else is a passive consumer, and the whole goal of the grid is to just distribute power from the center to the consumers. And moreover, they assume this idea of central control. There would be one company that controls the distribution, the transmission, and the generation. But in modern energy systems, we are facing with increasing challenges for which we will need new solutions. One of them is increasing uncertainty. You all know there is a lot more renewable generation on the grid, and this is intermittent, right? It depends on the wind and the sun. For example, a solar eclipse has to be very carefully planned in the European electricity system because they have to. There's so much solar panels that they really need to forecast what happens there. There's also a lot of new loads. We need to move to electrify our transport, our heating system, and so on. This example I will give in my talk with the widespread use of electric vehicles. There's also spatial distribution. So you might have a lot of loads in one area of the grid. So say you have a lot of EV charging in one area, and you have a lot of solar panels in another area. But the grid is not a copper plate, right? You cannot just assume that you can seamlessly transfer electricity from one location to the other without any problem. So if you live in the Netherlands, you for sure have seen it's all in the news, increasing grid congestion that we face, which is actually a big problem for the country, right? So many of the industrial projects cannot go ahead for this reason. And one that is maybe less obvious for a lay audience, but is very important, and we are tackling it in the research in my group, is decentralization. So increasingly, energy systems are no longer controlled by one party, but there are many agents that take individually autonomous and potentially individually optimal decisions that are good for them, but may not contribute to the stability of the system. For example, if I have an electric car or a battery, I will charge and discharge when I see better prices. I don't. That might not be the best time for the system as a whole, but this is the best decision for me. So then the question becomes, from if we look it from the multi-agent perspective or from a system design perspective, how can we assure stability and efficiency without the central control? So how can we design the incentives that to get this stability and efficiency without a central control? And of course, this challenge is no longer just an electrical engineering challenge. It requires knowledge from many fields: mathematics, computer science, but also economics and social science. But what I will try to illustrate here is the contribution that multi-agent systems can bring, and algorithmic game theory, and, well, intelligent systems in more broadly. Right. So before I jump into some of the challenges and some of the examples in energy systems, let me give a brief overview of the. Let's take a step back and look at the challenge from a methodology perspective as a complex socio-technical system with strategic agents. These are the kind of systems that we study in our group at CWI. So we are not just doing energy, although my talk today is about energy. But some of the challenges are common to many such systems. So they appear in many real-world settings, and some of these settings. Wait a minute. So the example I usually give when people ask me, okay, what is a good example that you can intuitively grasp is, let's consider the traffic routing in a congested city, right? So you have a lot of cars. They need to get from a source to a destination, and you have a number of roads, right? So if you could somehow centrally tell each of these cars which roads to take at a particular time, you'd say, well, everyone can get to their destination within a reasonable amount of time. There would be no problem. But what do you see in practice? In practice, at many times of the day, you see huge congestion in many parts of the network. And why is that? Obviously, because everyone is choosing the shortest route for themselves, right? But the problem gets even worse, or more interesting from our perspective, because you have this problem. So what would be the natural solution that you'd think about? Well, let's build more roads, right? Let's create some more capacity. And actually, this can make the problem worse, right? So if you build a road in the most congested part of a city, a new road in the most congested part of the city, this can actually increase congestion, not reduce it. This is the famous Brace paradox. Some of you might have heard about it. And why is that? Because everyone, or a lot of the vehicles that currently spread around at a number of roads will try to use this very popular new road, and that will just create more congestion in this area. By the way, this is, if you think that this is just a mathematical problem and it doesn't really happen in practice and so on, they have observed this in real cities. For example, there was an example, I think, about 15-20 years ago in New York. They had to shut down a small street that led into Times Square, and which was always congested. And they said, oh, well, we have to shut it down for repairs. And they would say it will be even more of a mess. But actually, what they observed is a couple of weeks later, the traffic actually improved because people the drivers learned to take a number of alternative routes. So there was less congestion. In mathematical terms, that was the edge in the Brace graph, right? So that's quite interesting to see. So such problems, okay, I gave this example with traffic routing, but such problems appear a lot in our electricity systems, in our smart grid systems, and I will cover some examples in my talk today, right? That's what the talk is about. But they also appear in other systems. Cloud computing is one that I also worked on a bit, where you have to allocate resources in a cloud. Crowdsourcing. So how do you incentivize people to form teams efficiently to solve a problem where everyone has just a part of the expertise that you need? Another project that we have in our group at CWI that's very important and is very relevant in today's world is the spread of this of online disinformation in social networks. So here you can again think that, like compared to 50 years ago, you can transmit information instantly. You can transmit basically information to anyone on Earth instantly. So it's much easier than ever in history to transmit information. But on the other hand, you have and then you say, well, people are most informed, but actually you have more disinformation than ever because people are spreading disinformation. So we really need tools and methods to address this kind of strategic behavior and to model this problem. Okay, so and kind of the one lesson that I want you to take from this slide, and maybe also from the talk, is that the optimal solutions that you might develop for a system with cooperative agents, with cooperative parties, might not actually be optimal if the agents are strategizing. Might actually be very far from optimal if people are strategizing what is the best for them. And this has many names in the literature. Bayes paradox, price of anarchy is another name for it. Comes in different flavors, right? So what I'm going to do now is give you a flavor of because we have limited time, but just give you a flavor of one problem in smart grids that where we addressed it and how we solved it, right? So so in terms of the smart grids, let me just kind of take a step back here. These are some of the problems that I worked on in my own research and in the research we do in our group at CWI. Electric vehicle charging is one that I'm going to talk about more in the rest of my talk today. Virtual power plants is another one. Virtual power plants, what are... Oops. Let me try to go back. What are they? If you have all these small prosumers with their own solar panels and batteries, how do we assure something similar in size and capacity to a big power plant? Demand-side response is another one where we incentivize lots of people to shift their consumption a bit to ease the load on the grid. And one that's very close to my heart, or that we do a lot of research in recent years, is peer-to-peer trading and energy communities, where we automate the way individual households can exchange energy with each other. Okay, so let's move on to the main example of this talk, just to give you a flavor of the kind of solutions that you can develop with multi-agent systems in this kind of domain. EV charging, right? So you all know about EV charging. Lots of countries have ambitious targets for rolling out EVs. These are some of the numbers. They are a bit outdated these days because things change. But okay, we have this challenge. We do roll out. Some countries are much more advanced than this. For example, Norway is almost fully EV by now. China is also doing a lot. Some countries are backtracking, but these are all these things. But the problem is that if you do have such a big rollout of EV charging, this will place unprecedented strains on existing energy distribution grids. So we cannot really handle this. And let me make that clear through an example. So consider this is a typical consumption profile of a home in Europe. Actually, this data is from the UK, but it can also relate to the Netherlands. This is from midnight to midnight. This is a night. You have some fridge cycles, very little consumption. You have some kitchen appliances in the morning. And the day you have this big peak with electric shower when this person comes home, and then you have some more kitchen appliances used in the evening, right? So what I'm going to do now is basically rescale the y-axis here, right? So I no longer have the demand from 0 to 30. From 0 to 10, but from 0 to 30. And what I'm going to do is assume this homeowner buys an EV, right? This is a very modest EV, a Lotus Tesla, and plugs it in around, comes home around late afternoon, early evening, and plugs in his car. So what you can see here is that basically the peak consumption goes up by a factor of around 3 times. And okay, you see this, so what's the problem? They pay for electricity and so on. But the problem is that if you have a neighborhood of, say, 50 to 100 houses connected to a local neighborhood transformer, which is typical setting in Europe, if more than 30 to 40 people buy an EV, because they all tend to come home late afternoon, early evening, this will exceed, most likely the peak demand will exceed the thermal limit of the transformer, right? So we cannot carry that, we cannot handle that. And you say, well, we'll replace infrastructure. What's the problem? But, well, if you think about you've all been around Amsterdam, I hope. You have these historic streets. You have some of the cables in the ground are more than 50 years old. So it's very hard to change all of a sudden, dig up all the streets and change all the infrastructure overnight. So we really it will happen, but but it's very expensive, and it can only happen gradually over time. So we really need a smart solution where we incentivize people to shift their consumption at a more convenient time, right? So how can we do that? Let's think about this problem. So let's think about the most common approach for this, which is called time of use pricing. So with time of use pricing, and there have been lots of practical trials and actually rollouts of this thing. Say, okay, we have a lot of demand in the evening because people are home and are also consuming electricity in their homes. How about if we offer much cheaper electricity after 11:30 in the night, right? Do you think this solves this problem? Since I asked you a question, obviously not. It actually makes the problem worse. Why is that? Because everyone who comes home in the afternoon and evening will just wait for 11:30 and just plug in the car then. It actually makes the peak worse. It shifts the peak, but it actually makes it worse. So simple type of use pricing doesn't really work. So what could work, and this is a solution that we've developed in my work that I'm going to talk about. So simple time of use prices are not effective. Is how about we ask each EV owner when they come home to report a deadline. I need my car to drive by this time because I need to get to work, or to give a talk, or whatever else there is. I can arrive home by this time, and this is the amount of electricity I need, and perhaps also how much I'm willing to pay. And then I can use some form of stochastic scheduling to decide which EV to charge when, based on which EVs are already in the system and which are expected to arrive, right? And there's many algorithms to do this stochastic scheduling. But in addition to that, we also need to assure that this report, what we call a report, is truthful, right? So people are not incentivized to plug in and out to try to search for the best price for themselves. So what is the solution we developed? Just to give, there's a lot of math in this and all of that. But just to give you a flavor of the solution, what we basically did, we used something called mechanism design. Mechanism design is a branch of algorithmic game theory and partially multi-agent systems to reward patient owners. So the idea is that you come home, you declare the maximum window in which you can stay plugged in, and the mechanism will guarantee you a price that is the best price that you could have gotten in this window. So if the best price was to charge between 2 and 3, and again from 5 to 6, and you need 2 hours of charging, that's how much you will pay, right? So the intuitive reason is that here the scheduling algorithm, if it has better availability windows, it can compute a much more efficient schedule overall, right? So this is work we did with colleagues at the University of Southampton in the UK and Harvard University in the US. And we came up with this smart scheduling mechanism and incentive mechanism, and that was very nice. But what we wanted to do a step more than that, and the step more was to actually test this with real data. Does it actually work? Would this mechanism actually work in practice? And we did have some real data. Luckily enough, we had data from a trial in the UK that gave 110 vehicles over 6 months to people to observe their behavior when they charge, discharge. So we can get some distribution information, and based on all this data, and we also had data from the loading of the grid when there would be more capacity available in the grid. And basically we showed that you can actually guarantee truthfulness. You can guarantee 95% allocation efficiency compared to offline. What does that mean? It means that the offline case is if you knew all the vehicles in advance and you knew all their constraints in advance, and you could just solve it offline. That is the optimal you could do. But of course, you cannot do that in practice because vehicles arrive over time. You don't know their constraints. But you can get 95% of this optimal allocation efficiency with this mechanism and guarantee truthfulness. So that was quite a nice result. And it kind of shows the kind of things you can do using a mechanism design and multi-agent approach for these kind of problems. Very quickly, I will say that there are many other settings you can look at. For example, we also looked at charging vehicles at distributed charging stations. The problem there is that if you think about filling a car with petrol, it takes a few minutes. There's usually no queue. But with EV charging points, there's usually just two, and it takes at least 30 minutes to charge an EV. So if there's two vehicles waiting there in front of you, right, there may be just two charging points in most street points, at least in European cities. You can wait really a few hours to charge your car, and that's not acceptable. So what we came up with is a system where vehicles signal to each other their intention, not just how busy a charging point is now. That is the first step, of course. You can transmit this information, but also what is your intention of driving towards each charging point. So if everyone leaves work at around the same time and start driving home, you know that other vehicles will arrive at a popular charging point earlier than you, so you might as well take another charging point. That's your best route. So by signaling their driving intentions, you can actually do much better for the system overall. There's a lot of information here. I mean, how we actually did this. It's basically a form of reinforcement learning and modeling the problem, the routing problem, as a Markov decision process, and so on. Just to say, we also use real data from the Netherlands to test this model. Other problems that I worked on are peer-to-peer energy trading in energy communities. How do you model these negotiations between prosumers that might exchange energy directly with each other? So I have a solar panel and my neighbor has a battery. How can we, if I don't use energy from my solar panels, can I trade with my neighbor so he can use it, and at some point I get something back from his battery? You can also look at this problem from a coalitional perspective, like if you invest in a joint asset, and then you can look at things like Shapley values and coalitional game theory. I saw there was a paper on Shapley values at this conference as well, looking through the program. They are hard to compute, but we have a solution to compute them to approximate them very efficiently in practice for an energy community. But these are some of. So we also used like a real case trial for that. So given the time that I see we are a bit of short, we can actually, and that's something about demand side response. Let me kind of conclude with a few thoughts about AI in energy systems that you might want to take away from this talk. So AI can be a useful tool, and distributed AI and multi-agent models can be a very useful tool to model these kind of large energy systems. Of course, they can be used to forecasting. So this is already used a lot, right? This is not. So, for example, because you have so much wind and solar on the grid, they already use AI for forecasting. So that, as you would expect, but they are also very useful in modeling the complex dynamics of such systems. That will tell us, if you design a system this way, will it be stable? Will you get congestion? What is the probability of a failure in the system, of a blackout? It should be very small, obviously, and so on. So modeling these complex dynamics is also one thing that agent systems and distributed AI is very powerful tool to achieve. One thing that I'm often asked is, I'm asked by electrical engineering, this, not so much by AI audiences, is, okay, but if you have this, if you have AI, what is the chance that it will replace electrical engineers and so forth? And actually, I see the opposite happens. We are not on they are not. I don't think that, at least in this domain, because it's so complex and there's so much details, we are not on the cusp of a super intelligence that will replace humans. In fact, demand for electrical engineers is increasing, not decreasing, because of all these problems. But basically, the challenge is no longer exclusive to electrical engineering as it was maybe 15, 20 years ago. And most large-scale projects in this area, successful large projects in this area, are strongly interdisciplinary. They bring the expertise from many different areas. And from the point of view of this community, which is, well, I approximate it to be distributed AI, multi-agent systems, and this line of work, and I hope some of you are in this community. Many of these challenges that are faced, we have worked on this. We have thought about such big distributed systems for a long time, and many of the challenges feel familiar. So even if you are not currently working in energy systems, but you're thinking, is this something that I want to look at? It could be a very nice area for you to apply some of the techniques that you are working on. So I think this is what I wanted to say. So yeah, I look forward to questions and maybe also meet.
But first, thanks much, Valentin Robu. Anything you would like to know? Any questions? Yes, see a few. I'll go in order. We'd like to know who you are and what your question is, of course.
So I'm Rafael from the University of Groningen. My question is, I don't know if it's possible, but if you could insert communication on the network, then it could have a scheme like I arrive at 6 o'clock, I plug it, but doesn't mean that I'm already charging from the grid. And then my system would communicate to the grid like what's availability, I would be in a queue. So when I wake up in the morning, I just unplug and I don't know even at what time was charged, like it's some kind of.
That's exactly the idea of our mechanism. That's exactly the way our mechanism works, right? So what we want you to do is communicate to us what is the biggest availability window, like the patient, what we call patients, that you can be there, right? And indeed, you don't actually, you tell me you can be there from 6 o'clock to 9 o'clock tomorrow, right? And you need 3 hours of charging in this, I don't know how much is that, 18-hour window. But you don't. I cannot guarantee which hours you will charge. But what I can guarantee you is that I will give you the price, which is the lowest price you could have gotten by choosing trying to game the system or choose the hours yourself, right? So basically, because what will happen is if everyone communicates with the stochastic scheduling or with or smart scheduling, if everyone communicates their best availability window and constraints, because some people really have to leave in a few hours, right? They really have to do that. So we have to prioritize those people, but most likely those people will have to pay more, right? So because they have a lower availability window. So the fact that you can wait 9 hours versus waiting 3 hours means that in expectation you are much more likely to get a better price than the guy that says. So if you come in and say I need to charge it now in the next 3 hours, okay, we can accommodate you, but you will pay more than the guy that's patient and is willing to.
Oh yeah, but how the communication happens? That's
the communication. Basically the way we have designed it or we envisage it, there is like an auctioneer, like a central planner, right? And basically each EV. I mean, first of all, the human driver can also input this data when they come home, right? They can also change this data, but we can also learn this data over time, right? And then the human driver can adjust it, and then each EV will communicate these constraints when they arrive home to this central planner, right? I have to leave by this time. I need this amount of electricity. This is how much I'm willing to pay, right? And this information just goes on whenever each vehicle arrives to the central planner. And when new vehicles arrive, the central planner will adjust its plans, right? We'll revise it because it's not the one, we don't just design the schedule once. We redesign the schedule each time a vehicle arrives. It's a dynamic problem, right? So each vehicle communicates its constraints when it arrives. There is a replanning, there is a recomputation of prices and incentives, and that's basically the idea of how the system works. Yeah.
Thanks so much. We have another question over here. Once again, can I pass in the behind? Thank you. Yeah. Who are you? How can we help you?
Hi, I'm Tanya from Plaksha University, India. So I just wanted to know a bit more about your MDP formulation. What are your states and actions, and how you design that?
How is
The MDP, the Markov decision process formulation for your EV.
Oh, yes. So we use Markov decision processes for the routing part. I mean, the slide is. By the way, all of these are 1-hour presentations, right? So I've just kind of given flavor here. So the idea is that you model the road network as a graph, right? And each road segment has some traffic or some expected traffic. at that kind of the day. So that gives a probabilistic delay, right? And there's also these back loops of waiting at charging stations, right? So there is a delay in each. So basically, you model it as a graph problem, as a problem of traversing a graph and getting from A to B, right, from your destination. But in the meantime, you might also have to visit a charging station, right, and wait there. So all these delays or expected delays form a Markov decision problem, a very big one, right, of where you go. So obviously, as you know, Markov decision processes are very expensive to solve. You need a lot of computational tricks to make it work in a big simulation, which we have done. But that's kind of the idea, right? So you model traversing each segment of the road as a one decision, and then the stations are also one decision. So yes, and then you solve this for each EV, and then if they have extra information to solve their MDPs from other EVs, they can do it a bit more efficient. Yeah, thank you.
Yes. Who are you? How can we help you?
Hello, everyone. My name is Natasha. So I was actually going to ask the first two questions, but one excellent presentation, I think, is a very great way because it's very time efficient, energy efficient, it's dynamic, it's targeting a lot of the things that we're dealing with right now, especially when it comes to energy with the boom of AI and then, the vehicles. So yes, to go back to the questions, I was gonna ask about the stochastic process, but I think I have a better idea of what you just explained. So basically, you have the delayed, and then how it's incentive based, correct? And also like they will be able. So the trick here is that like people will let you guys know like the availability window, and then based on that, you will do the probabilistic model to let them know, hey, if you charge around this time, you will have the lowest price. And then it'll guarantee that everybody like gets a best price, with low energy for everything else, right? It's a great idea, and I really like it, so I had to just let you know that.
Thanks a lot. Thanks. I think you got it very correctly. And just to add that you also need to incentivize them to be truthful about the deadline. So if you think that you are going to get a better price by reporting an earlier deadline, you could do that because you could just unplug your EV. So actually, you always get a better price by being more patient, right? Because in expectation, there is some chance that in the extra hours you might observe a better price. So these incentives are also very tricky to design, right? So yeah.
Okay, and then question. So how do you penalize when they lie, for instance?
They can lie. It's because actually we don't know if it's a lie or not, because some people actually need their car earlier. So we don't have a camera to see if they are home or not. They can just, but they will in expectation pay more, right? So the less you can wait, the more you will pay in expectation. That's a guarantee, right?
Thank you very much.
So,
Thank you.
Okay. Other questions or compliments? Welcome to. Yeah, sure.
I'm Shalini Sarode. I have a question following up on her question. So the incentivization is based on the communication of your scheduling, right? What if the scheduling doesn't happen, or like the communication is broken, or something like one agent does not communicate that this is when I need the charging?
So you communicate your constraints, not your schedule, right? So what happens in the way we design it is that when a vehicle arrives, it plugs in, right? And that's the arrival report, right? What you call the arrival report. That's when I arrive, and then you have to report that I need my car by this time, right? If you make a mistake and say I need it earlier than I actually need it, because then the system will wait for a report for you, will ping you to ask you when do you need your car by, right? So it will try to make several attempts, right?
But let's say there's no connection, there's a problem, there's no internet. Will it refer to default based on learning, or what will it do?
You can think about it that way, but basically, if a car is available and is plugging in, the system will try to get a report or some information from it, right? I mean, anything is possible, right? The plug can malfunction in that way, so there's lots of things that could happen there. But the system will try to get a report from you, right? So if it's earlier than actually the real one, you'll get charged earlier, but you'll pay more than what you should pay. If you make a mistake that it's later and then you are not charged in time, well, then you have to take the taxi, because then that's a malfunction of the system. I mean, of course, communication systems can fail, but basically once you come in and you plug in your car, the system will know that you are there, and it will have to try to get some information from you. But the important thing is just the other thing. One thing that I'm asked is, well, what happens if people don't have the patience every day to communicate their constraints? And then you can learn. So actually, the way the system is designed is that there is a learning agent that looks at the distribution of your driving per day, and has a standard value that will be communicated, and then the driver can just override that and say, no, tomorrow I actually need it much earlier, or tomorrow I don't need to go to work.
Valentin, I'm going to make it very practical. So let's say we have an internet problem. There's no internet. I come home, I plug in my car. Will it automatically charge? Will it wait, or will it conform to the schedule learned based on previous behavior?
Yeah, I mean, that's a problem, right? So in this modern, you do assume there is some communication eventually. I mean,
Let's say there's not. Is there a backup already, or does that still need to be built?
It still needs to be built, but
That's an answer.
you could have a standard assumption where you say, because you know which EV is there, right, at this house, and you know its typical distribution over the previous months or several months, you can just use a value which is inferred from that distribution. That also works, and that actually is happening. I mean, that's the way we envisage the system now, right?
Yes.
So, but the driver can always override and say, no, tomorrow I actually need it much earlier, or I don't need it.
Makes sense.
So that's going back to that point. So I guess when, based on what they just mentioned, I guess at some point, you guys could have just like your own agents where they can self-adapt, self-learn based on the behavior, because you already are building that history, and then based on that probability, you'll know, okay, Natasha usually charges around this time. We have like data for like a whole year or two.
Yeah, we do have.
So this is what Natasha usually does. So it learns. So and because you also mentioned the distributed, multi-agents AI, distributed AI, multi-agent system. So some point it will self-adapt, self-learn, make its own decisions, and you just already have the data. So maybe you won't even need them to always like let you guys know through the system.
Correct. So we actually do have data, right? I mentioned it at the end of the slides that we have data from a real world trial of 110 vehicles, which we have used for learning. So indeed you can operate a system like that, but you also need to allow the driver because, for example, you can say I usually go to work arrive at 10, but tomorrow I have to be there for 8, right? And then I have to have an override way to say, no, tomorrow I need it for 10. Or some people have some days they have to go to work, some days they don't. It's more changing schedule. So dynamic stage. So you always need to give the driver a way to override what is being learned, but you can use a standard value in the rest of the days.
Yeah. Makes sense. You mentioned that if people want to engage you in conversation or have questions, you will be here during the break and during the lunch as well, and you're more than happy to engage.
I
Correct?
I'll leave after lunch, but I'm very happy to talk to you about what you're doing, and
Excellent. Thanks for now, Valentin Robu.
Thank you very much.